Hello everybody. I'm going to try and give you a little lesson here on Bohr models and Lewis dot structures. So first, this is chemistry. Yay. So review. Basic unit of matter is the atom. Atoms have electrons outside the nucleus, and of course your protons and neutrons are inside the nucleus. So up until now, we've talked about the electrons being outside the nucleus, but not really any information about what they're doing or how they're doing it or where. So this quick review here again, electrons are those negatively charged things orbiting around. Protons are the positively charged things in the nucleus. Neutrons are neutral. When you look at your periodic table, which hopefully you should all have in front of you right now. If not, pause this and go get your periodic table. So your periodic table has this atomic number at the top, and we know that atomic number tells us the number of protons. And we learned in the last chemistry chapter that if it's an atom and it's neutral, so we're talking atoms here, not ions, then the number of protons is equal to the number of electrons. That is what we're going to use for this lesson. We're just going to assume they're all neutral atoms to calculate number of electrons. Of course, mass is protons plus neutrons. In the past, we had specific isotopes. Today, if we need to calculate neutrons, we're just going to take this number and round it to the nearest whole number. So we'll just call this 16. And then we'd say 16 minus 8 would give us 8 neutrons as well. Uh-oh, what just happened? Okay. So then, next slide. So here's our periodic table. And here we just have atomic numbers. I just wanted to let you know the things you might want to write on your periodic table. So the line right here, if you're in the classroom, you can look at that little stair step down this periodic table on the side wall. That's the line between metals and nonmetals. And these purple things are what we call metalloids. So they sometimes can act like a metal or a nonmetal. The yellow things are all metals, and the green things are nonmetals. And yes, hydrogen's over here. Sometimes it seems like one of these. Sometimes it seems like one of these. We'll talk about it later. At the top, notice the numbers. As we mentioned before when we studied ions, everything in this column tends to lose one electron and become a plus one ion, cations, right? Everyone in this column tends to lose 2 and become a plus 2. These are much more complicated. We'll talk about them later. These metals tend to lose 3 and become a plus 3. Over here, they tend to gain 1 electron and become negative 1s. These are anions, right? These tend to gain 2, become negative 2. These tend to gain 3, become negative 3. This row has a mixture of things that could gain or lose 4. So that's what these numbers are. Your noble gases, of course, they don't do anything like that. They don't gain or lose anything. They stay neutral. Now, the Roman numerals at the top here are telling you the number of valence electrons. Now, we're about to learn what that is, but you can go ahead and write it on your periodic table now. There's 1 valence electron in this column. Everything in this column has 2. These all have 3. These all have 4, 5, 6, 7. And these mostly have 8, except for helium, which only has 2 electrons, so it only has 2. All right, so that's the basics on here. Hopefully you have taken a minute to write things on your periodic table at the top. It will be very helpful to you in a few minutes. If not, pause the video and do that. A little bit of vocab about the periodic table. So when we talk about the rows going from right to left, those are called periods, okay? So periods are going to match up with our energy levels. Energy level 1, period 1. Energy level 2, period 2, 3, 4, etc. Up and down, we call these vertical things groups. So they're going to have, some of them have their own special names. Like I already said, these are the noble gases over here, right? They'll all have names. We'll get to that later. I won't waste time here. So the Bohr model. Now, Bohr came up with this nice little model to tell us where the electrons are, since this is forensic chemistry, I am not going to go deep into how Bohr is wrong and the s and p and d and f orbitals and how things really are. But even though we know it's not accurate, it's still a nice representation of how things are. So we will draw the Bohr models in this class, and we'll learn to draw Lewis dot structures, and that will help us understand bonding, and that's all we really need on this level. So, proposed by Niels Bohr, 1915, electrons orbit the nucleus in orbits. Okay, we're going to call them orbitals or energy levels. They have a set size and energy. Now, I understand that it's not really like planets around the sun, but it, again, gives us a nice two-dimensional way to represent things. So the lowest energy is closest to the nucleus and has the smallest orbit, and then further out here would be higher energy. So if you think about horses racing around the track, you'll use less energy the closer you are to the track, right? And more energy if you have to move out. So energy levels, when two atoms approach each other, their nucleus do not touch. Only the electrons are involved in chemical reactions. So the nucleus are protected by those electrons outside them. When you feel like you're touching your table or touching your desk, it's really just those outer electrons interacting. So Bohr diagrams, first you need to find out which period you're in. Okay, so you're in row 1, that's period 1, 2, 3, 4, etc. So elements in the first period, they just have one energy level. Elements in the second period, they're going to have two, and so on. Things get much more complicated down here, but again, this is just forensic chemistry, so we're going to keep it simple. So Bohr model rules. You just show the electrons with the energy levels. So the first level can only hold 2 electrons. It only has an s orbital. So if I talk about that in class, that's what we're saying. S orbitals can only hold 2 electrons. It only has an s orbital, so it can only hold 2. Now the second energy level has an s orbital and a p orbital. S's can hold 2, p's can hold 6. So the second energy level can hold 8 total. The third energy level has an S, a P, and a D. So S's can hold 2, P's can hold 6, D's can hold 10 for a total of 18. Things get a lot more complicated when D's are involved. So for right now, in this class, we're going to stick with the 2-8-8 rule. So think level 1 holds 2, level 2 can hold 8, level 3 can hold 8, and that's probably as complicated as we're going to get for now. All right, so let's practice drawing some Bohr diagrams. So I am going to get out of this program and go to my Jamboard, and you will have to excuse me on my drawing. I'm just not all that great at it. You should have a worksheet right now. Hopefully that's been handed out, and you will, on one side of it has practice Bohr models and practice Lewis dot structures. So the first one is for hydrogen. So we're looking at hydrogen here. Hydrogen has 1 proton, generally no neutrons. There's no mass on here, but it has it has a mass of 1, so no neutrons. Now we want to draw a Bohr model for that. So give me a second here. Make sure I got my pen. Now we'll draw the nucleus. Oh, that's terrible. With 1 proton in it and no neutrons. All right, then I'll draw the first energy level here. Pretend these are circles. And since it only has 1 electron, I'll just draw 1 electron. And that's your Bohr model for hydrogen. That's all there is to it. Now, if I go to something, you have to write, this is hydrogen. If I want to do something more complicated, let's go back to our periodic table and take something from row 2. So let's do boron. Okay, so boron has a total of 5 electrons. So that's what I'm going to place. Now, if you look on your periodic table, I believe, if I remember correctly, the mass is closer to 11. So we'll say it's boron 11. Okay. So let me go over here and say we have boron 11 with 5 protons in it. So inside the nucleus, I'm going to have protons equal 5. My neutrons will equal 6. Okay. Now, energy level 1. Again, all there is an s orbital, so I can only hold 2. There's 5 total. There's going to be 5 electrons total, so I'll put 1 here. I can put 1 here. And that level's full. So then I'll have to go to energy level 2. And there'll be 1, 2, 3. When I place mine, I generally do like kind of north, south, east, west. So 1, 2, 3, 4. And then if they have enough, they pair up after that. And that'll be similar to how our Lewis dot structures are. So there's one for boron. Now, if I wanted to get something from the third level, let's say magnesium here. Magnesium has 12 total electrons. So let's say we got magnesium and has 12. Let's say it's magnesium 24. I was going to put a 24 up there. I got to thinking. All right. So my nucleus would have protons equal 12, neutrons equal 12. Sorry, it's hard to write on this thing. All right, so I got 12 total electrons that I'm going to place. First energy level can only hold, that's right, 2, and it's full. The second energy level can hold up to 8. So I'm going to go 1, 2, 3, 4, and then again 5, 6, 7, 8. Now that one's full, but I have a total of 10 so far. I got 8 out here, 2 in there. So I need a third energy level that's going to hold 2 more. 1, 2. So that's a total of 12. All right. So that's all you have to do for the Bohr models. So on your worksheet, it asks you to draw the Bohr models for these. So hopefully you can go back and watch it again if you need to figure that out. Now, let's go and look at Lewis dot structures. So it turns out when we're concerned about bonding, we really only care about the outer electrons. So the outermost electrons are called the valence electrons. So back on your periodic table, when you wrote these Roman numerals, that's how many valence electrons everything in that column is going to have. So let's look at magnesium here. Remember how we just had 2 on the outer level? So there's 2 valence electrons. When we drew hydrogen, it had 1 on the outer level, 1 valence electron. When we drew boron, it had 3 on the outer level. It has 3 valence electrons. So that is what we do when we do Lewis dot structures. Things get a lot simpler. All we're really concerned about are those outer valence electrons, so we find a way to write a quick symbol that just tells us the valence electrons. But it also shows us about lone pairs that might exist. So that is why I was doing the north, south, east, west thing and kind of pairing things up that way. But the important thing is we're only showing valence electrons. So Lewis dot structures, first, find out which group you're in. The first group is always going to have 1. The second group is always going to have 2. This group will have 3, 4, 5, 6, 7, 8, except for helium. Helium will only have 2. So let's go back to those things that we were just doing, looking at their Bohr ones. And now we're going to do a Lewis dot structure. So a Lewis dot structure, you will start by just drawing the symbol. So, let's see. There's your Bohr model over there. This would be the Lewis. I just draw H, okay? And I say, well, how many valence electrons does it have? Well, it just has one. So I just pretend that there are 4 sides around this H, right? North, south, east, west, like I said. And I'm just going to write 1 dot. Does it matter if your dot's here or here or here or here? Not really. These are 2-dimensional versions of something that's really 3-dimensional, so it doesn't really matter. What matters is you put 1 on each side before you pair them up. Now, this one only had 1, so that's nothing to pair up. On the boron, for the Lewis dot structure, I would just draw a B. Okay. It has 1, 2, 3 valence electrons. So I would draw 1 dot, 2 dot, 3 dots. Done. On the next one, remember you're only doing the electrons that are in the outermost ring. This outer ring only has 3. Here's magnesium. It has 12 total electrons, but only 2 of them are on the outer ring. So it has just 2 valence electrons. So its Lewis dot structure would just be Mg. Sorry, that's a terrible M. And then 1 dot, 2 dots. If I had something that had, let's pick something with, let's say chlorine, right? So chlorine, I would draw Cl. And if I go look at chlorine on my periodic table, I'm going to use this one because it'll tell you how many valence electrons it has right there. So here's chlorine. Chlorine has 7 valence electrons. So I'm going to need 7 dots on the outside. I'll go 1, 2, 3, 4, and now I can pair them up. So that's 5, 6, and 7. So what's coming is we're going to talk about like how many unpaired electrons does chlorine have? Oh, there's 1 without a partner, 1 unpaired electron. This will be where chlorine wants to bond. What'll happen, so here's a little flash forward. Let's draw one for sodium. N-A. Sodium just has 1 valence electron. Boop, right here. And what we're going to learn in the future is that everybody wants a full valence shell. Chlorine just needs 1 electron right here. Sodium would like to get rid of this one, and then it'll go down to its inner shell. It's full. So it is going to give this one away to chlorine. Chlorine will say, oh, thank you. Now I'm a -1 ion. So it'll be like, oh, thanks. Now I'm a +1 ion. That's terrible. +1, but you know what it is. And now they're going to make an ionic bond that way. So that's a little flash forward to where we're going. You'll be able to use these Lewis dot structures to see how things bond. Now you should be able to complete the worksheet. You're going to do Lewis dot structures on the back where it kind of looks like a periodic table. And good luck.